So if we can just revise this Kmeans clustering algorithm one more time, I mean, it's very important to know some unsupervised algorithms because most of the data around us is unsupervised. So once we have reduced the set of original features to a smaller and a more manageable set, we can find interesting pattern by grouping similar instances of data together into clusters. Kmeans clustering can help us to do this using the features, only the features. So we specify number of desired clusters. It's the user in fact whose algorithm. You need to decide how many clusters do you want. So you need to get some knowledge about what kind of data set you are working with, because this is domain knowledge. How many clusters? If we are working with iris data set, so it's known that it's 3 clusters, for example. And the algorithm will assign each example to exactly one of these K clusters. So we decide how many clusters. For example, K equals 3, K equals 5, K equals 2. And after that, the algorithm will try to assign each data point into one of those clusters. To speed up this clustering process, Kmeans randomly assign each observation to one of the K clusters and they begin to reassign these observations to minimize Euclidean distance between each observation and its cluster center point. In fact, there are many ways for implementing this one. So here he mentioned that we just divide the data by random and assign each part to one cluster, and after that we assign it according to the Euclidean distance. Another way also to select K data points. We have many clusters, maybe 100 points. We select K data points and we use those 3 data points as the centroids of each cluster. And after that, we pick the first point, calculate Euclidean distance with those 3 centroids, and we will assign it to the closest one. And when you decide this, you will update the centroid. The centroid will move a little bit in the middle between the two, I mean the first one and the second one. In this way, you can see that the centroid is moving until some point where there is no change. We can just say that we are finishing now. So as a result, different of Kmeans, each with randomized start will start in slightly different, of course, each time. I mean, in this approach, each time we should expect, if you didn't fix it, if you didn't fix the random seed, each time you will get slightly different centroid, for example, right? From these different runs, we can choose the one that has best separation, defined as the lowest total sum of within cluster variations across all K clusters. So we need to run it different times, for example, several times, and after that, we select the one with the smallest or the lowest total sum of within cluster variations, because we need at the end to get, I mean, clear clusters and good separation between different clusters. So I applied this algorithm. We can apply it using sklearn models. So we can get sklearn dot cluster, sklearn dot cluster. So we can get Kmeans cluster from this sklearn dot cluster. And this is, I selected the first 2 points.
2 attributes.
2 attributes, 2 features, correct. So I selected, I mean, it's a third and fourth, right? Features. And of course, so we have X, we have Y. I just normalized it. It's very, very important to normalize here, in fact, because if you have 2 features and I don't know, maybe you can test it with normalizing and without normalizing, but normalizing is very good. So we split the data, we stratify to get balanced. Stratify here means we need to get balanced. All classes are balanced or represented equally in the training and testing data set. So this option here, it's very, very important to get balanced data sets. Test size equal 0.3, which means training size will be 0.7. From those 0.7, we can take one part for validation, right? We divide the data into a training set and a testing set. From the training set itself, we can get part for validation, right? Yeah. And validation set, it's important to tune your hyperparameters. Hello, Ahmed? Yes. So we will apply Kmeans clustering here. I just selected random state equals 7. We will fit the data. We will fit the model into our data. It's unsupervised. So just use Xtrain. We use only features, right? We use only features, or we don't care about labels. Labels are not important here. I used labels only for testing the accuracy of the algorithm. But in the clustering process, we are using the attributes or the features, but we are not using the labels.
That is unsupervised learning.
It's unsupervised learning. Yeah. So if you can notice here, each time we use Xtrain, Y-train, correct. But in this case, we are using only Xtrain because it's unsupervised algorithm. So finally, we will have the centroid. We can print the centroid. We selected k equals 3. So in this case, we should get 3 centroids. I'm just testing the accuracy of the algorithm using the labels, right? But this is not the case. It's just because we are working with a toy problem here, for example. And after that, we can run it. So finally, we got 3 clusters, and those are the centroids of each cluster. So after running this algorithm, you will get k3 center points. So it's different from the k-nearest neighborhood. In k-nearest neighborhood, it's supervised, right? K-nearest neighborhood, it's supervised, and we need to keep the data, all data points with us all time. You need to put it in a bag and just carry it with you all time. When you have a new data point, you need to compare it with all data set, all data points which you have. So you need to keep it with you all time. So k-nearest neighborhood, it's very, very expensive in calculations and in terms of memory, not practical, right? Because if you have millions of data points, so it will be impossible to use it, in fact. It will be very tough because we need to keep all those data points with us all time.
In each iteration?
In each iteration, when you have a new example, because I compare this, when you have an example and you need to classify it, you compare it with the rest of the data points using a key neighbors. So how many neighbors? So I need my neighbors. If you don't have neighbors, you will not be able to classify, because I don't know which part should we keep. And you can say, okay, if I can predict in which location, in which I can keep some data points, for example, but who knows? I mean, you don't know the distribution, if the next point is coming from which distribution. So you need to keep all neighbors, you need to keep all data points. But in this algorithm, when we run this algorithm, we will get k center points. So after running it, we don't need to keep any data points, we just need to keep those centroids. Now I have 3 centroids. So imagine I got a new data point here. I need to classify it. So we will calculate the Euclidean distance between this point and this centroid. This centroid. And we will associate it to the closest one. So maybe this one, this is class 1, this is class 2, this is because we don't know labels, we don't know names. This is something also very important. So the user, he must go and say, okay, this is versicolor. This one, it's, we have 3 clusters, versicolor, Virginica, correct? So you need to go and label this one, for example, correct? It's the same for email spam, for example, classifying an email into spam and ham. So this one will be spam, this one will be ham. You need to go by yourself and label it. You need to give it a label one time, right? And if you got a new example, which we need to classify, we will calculate the Euclidean distance between this point, the new point, and the 3 centroids. And we will associate it to the nearest one or the closest one. If it is closer to this one, it will be this cluster. If it is closer to this one, it will be this cluster, and so on. So this algorithm, this is very, very nice algorithm. This is one of the best algorithms, in fact, Kmeans cluster. Kmeans clustering also, it has lots of application. I mean, especially working with data, when we try to extract some rules from the data, we use Kmeans clustering. And there are many versions. There are lots of versions from this Kmeans clustering.
Just I remember what you said last time. You have to make sure that the points that you are going to choose representative of every class. And the beginning should be correct.
Yeah, it's a problem. We have one problem here. So because this algorithm starts with k random points from the data set. So imagine we will be very lucky if we got data point here, data point here, a data point here. So in this case, we will get a distribution and we will get 3 clusters. But the problem will occur if we selected the 3 data points very close from each other, from that part, for example. It will be hard to cover all data points, and maybe we will end up with, one cluster or something. It will be very close to each other. It will be 3 clusters as well, but maybe just at the same point. It happened before with me, in fact. that you get the 3 clusters located in the same place. So there is some kind of overlap, and it's not correct. So it's very important here to just run this algorithm several times, and each time you check your results. If you got really good separation between classes, and also this low variation within each cluster, we need to get this number, and this number will help us. So this is the lowest total sum of within cluster variations, right? Because if imagine if in this example I got all my 3 clusters centroids here, it can happen, identical points. So we can end up with 3 centroids, 3 identical centroids. The variation within this cluster, it will be very high, because I will have some points here belongs to here, some points here belongs to here, so the variation will be very high. So we try to minimize this coefficient. You can say this is a cost function, which we need to minimize. So we need to calculate within cluster variation for each cluster, right? And if this number is very large, just repeat this process several times until you get a smaller one. So it's very, very important here to run this algorithm several times, and each time you need to check within cluster variation. If this number is very high, it means no, because maybe those 3 clusters are identical, and we just associated some points to each cluster, but they are located in the same place, right? So it's so this is the only problem within this algorithm, right? Because when we initialize the algorithm, people online, can you hear us? Hello, can you hear us, please?
Yes, they said yes.
Okay, very good. So I don't know. Okay, they can see. Yes. So the problem in this algorithm, it's a very, very good algorithm. It's unsupervised. Unsupervised learning is very, very important. It's much important than supervised, in fact, because in supervised learning the problem is very well defined, but in unsupervised it's not well defined. And when it's not well defined, you should expect that you will get strong AI. If we can, classify AI into strong and weak, when the problem is very well defined, it's weak AI, right? Because, for example, I need to build a machine learning for classifying fish, for example, according to size and maybe shape and stuff like this. So it's very well defined the problem. I will collect a data set. We will label this data set. So we will build a machine learning within very narrow domain. So we call it weak AI, because the problem is very well defined. I give you a task, very clear task, right? And I give you, descriptions and protocol, for example, for solving it. You need to do this and that. Step 1, step 2, step 3, step 4. So what is left for you? It's very simple. You just need to follow it step by step and you will do it. So we call it it's weak AI. But in case of unsupervised, you should expect that it's a strong AI, because the problem is not well defined. So it's more challenging and unsupervised, but it's more promising as well. Yes.
I think it's just possible to improve the method or approach by cleaning data. It's not possible to change the, for example, Kmeans algorithm. Yes, it's just possible to cleaning data better or not.
Yeah, cleaning the data, it's something which we need to do.
For example, we get a result, but it's not favorable for us. In order to get better result, we have to change the data, or we have to change the algorithm.
No, you cannot change the data, right? So
no,
processing.
Yeah,
it's just normalizing. We need to normalize the data. We need to fix missing values and so on. So there are something standard which we need to do for any algorithm. So I need to prepare anyway my data. If I will go for supervised or unsupervised, we need to clean the data. We need to fix missing values. We need to normalize. We need to standardize. We need to use BCA, for example, to reduce the set. We need to use Autoencoder to reduce the set. Right? Because imagine that there's a problem here also in Kmeans clustering. If you have big number of features, it will be really very difficult, because calculating this Euclidean distance will take time and it will be difficult. So you need to maybe get a reduced set of features. You can try to use BCA. If you have 10 features, maybe it's hard. I need to visualize the problem. It's difficult to make those calculations. So maybe it's smart to use BCA. for example, and they get a reduced set of features and work with those small set of features or reduce the set of features. So, because anyway, you need to clean your data. But the algorithm, of course, I mean, you can make some changes in the algorithm, but you can develop it by somehow randomization. How can I initialize my initialization is very, very important, right? It will have huge impact on the algorithm. And to avoid this, I mean, to get rid of this, you need to run your algorithm B several times and just to try to check those within cluster variations. This number, if this number is going down, we need to minimize this number, right? If you can minimize it, if you can get some clusters with small within cluster variations, it will be big achievement because we just say, okay, now I'm happy. This solution is good. Because it's very important to differentiate between two solutions. If I run my algorithm 10 times, what is the difference between each time? We need to get some metric to differentiate between each solution. So within cluster variation, it's very, very important. We need to reduce within cluster variation because at the end I will have 3 different or k different clusters with unique structure and right?
Yeah.
But if this variation is too high, I mean, there is no need. I mean, if we are studying in a classroom, for example, and we have people from physics, people from chemistry, people from philosophy, people religious studies, language, and machine learning, it will be very tough really to have identity and to try to say that now we are studying something specific. So we need to cluster ourselves. We need to reduce within cluster variations, right? If we are all interested in machine learning, for example, in a classroom, the classroom will be fantastic because people will be motivated, working hard, because all of them in the same page, all of them are motivated, all of them have great interest to study this area. So this is what I mean within cluster variations. When we reduce this within cluster variation, life will be much easier because it will be easy to define things. Mm-hmm. So I mean, maybe also how we measure the distance, right? So if we are using Euclidean distance, Manhattan distance, so this is also something very important, right? How we measure Euclidean distance. You need to try, it's hyperparameter. If you will decide to go for Euclidean distance, if you will decide to go for Manhattan distance, right? So there are many ways for this, and it's easy to implement the algorithm. Maybe I remember a long time ago, people they try to use fuzzy Kmeans clustering. I mean, even if they go for rule-based something, fuzzy Kmeans clustering. So there are many versions and lots of implementations of this algorithm. So last time also we have been talking about autoencoder, and we will talk before about PCA. PCA is a statistical tool for dimensionality reduction, and in PCA, principal component analysis, we try to get eigenvectors and eigenvalues, and we will get the same number of features, for example. So if you have 10 features, you will get 10 features, but it will be more. It will be 10 eigenvectors. And each eigenvector is perpendicular to the other eigenvectors. And you will have some eigenvalues. Those eigenvalues will represent the variation of the data in that direction, right? And we will sort them down according to the eigenvalues. And we will pick maybe the most important 5 principal components, and we will use the set for reconstructing the data one more time or for training your model. And it's very important, very important to work with a reduced set of features. When it's reduced the set of features, your model will be simple, and when it's simple, you will avoid lots of problems, right? Such as overfitting. Overfitting, it's a catastrophic problem in machine learning because sometimes you cannot get rid of it. It's really something tough. It's nightmare. So when you are working with a reduced set of features, you will be working with the most interesting features, most representative features, and your model will be more simpler. And then when it's simple, we can say that we will avoid lots of problems, such as overfitting. So the autoencoder also, we can use the autoencoder in the same way for dimensionality reduction and denoising. In fact, we can use it for denoising and the dimensionality reduction. It's a feed-forward neural network, so it's not recurrent neural network. It's feed-forward neural network, where the input is the same as the output. They call it unsupervised because of this. But in fact, in terms of calculations, it's not unsupervised. But for the data, I mean, from data point of view, it's unsupervised. But from algorithmic point of view, it's just supervised algorithm, correct? Because we have some inputs, we have some outputs. We have some outputs. And then we will calculate here reconstruction error, and we will use this reconstruction error. It's similar to the prediction error. But because here we are not predict, we reconstruct. So it's feed-forward neural network. It has an input image, and the output also is an image, correct? The first part, it's encoder. It consists of encoder and a decoder. And in the middle part here, we call it bottleneck. And in this bottleneck, we try to generate a code. This code will be a reduced set of it's a code of the image, original image, or a reduced set of features, for example. So maybe if we are talking about this example, for example, we have M-list data sets. Here it's 28 times 28 pixels, which is 784 inputs. So the output will be as the same as the input, and in the middle here we will have the code. You can decide the code. It could be 32 bits, right? If we selected in this example here, I selected this bottleneck or the code, a vector of 32 values or 32 bits. So in this case, we are reducing the image from this original shape into this code, right? So the code will be a reduced set of features of the input. So in this case, instead of training a model with the original input, I will train a model with the code. So we will simplify it. And when we simplify it, it will be just easy to train, and we will not need too much data for training our model, and we will try to avoid overfitting. So it consists, so they compress the input into lower dimensional code and then reconstruct the output from this representation. So we in fact, we encode and decode, right? The code is compact summary or compression of the input. So in fact, we can use it for data compression, right? And when we compress data, life will be easy. Even if you want to transmit the data to somewhere else, it will be easy. And on the other end, we can just reconstruct it one more time. The autoencoder consists of three components. It consists of encoder, code, and the decoder. The encoder compresses the input and produces the code, and the decoder reconstructs the input using this code. So this is the whole task. So we train, in fact, a feed-forward neural network where the first part encode the original image into a subset or a reduced set of features or a code. And after that, the decoder will try to reconstruct the same image using this code. So it's just, so this one compress, this one reconstruct. And at the end here, we need to train this one because we will initialize, because this one, it's a feed-forward neural network, and feed-forward neural network has some weights. We will initialize it with random numbers, and we will calculate the reconstruction error here, and we will use the reconstruction error for adjusting the weights. It's just feed-forward neural network. No difference at all, just the same. So the autoencoder learns a new representation of the original input data via the encoder to minimize the reconstruction error between the newly reconstructed data via the decoder and the original input data. Autoencoders are mainly for dimensionality reduction or compression algorithm. So we use it for dimensionality reduction or compressing the data, and it's data specific, which means when it's data specific, when it's designed for a specific problem, we need to use it within this domain. We cannot use autoencoder, we cannot use maybe transfer learning here, right? Because it's very data specific. So we are doing it for, if we are doing it for MNIST data set, we cannot transfer it to a more complex problem like CFAR 10 or CFAR 100, for example, right? Because it's more data specific. So we cannot expect the autoencoder trained on handwritten digits to compress landscape photos, for example, right? It will be, and it's lossy, which means the autoencoder will not be exactly the same. The output of the autoencoder will not be exactly the same as the input. It will be a close but degraded representation. I mean, the constructed image all the time, it will be like noisy image from the original image or degraded image. The quality will not be the same because and it is the same in principal component. So if I have in this specific problem 784 and I use the 100 features principal components and I try to reconstruct the image the reconstructed image will not be the same as the original image. It will be degraded version from the original image. So unsupervised, it's unsupervised because to train the autoencoder, we just throw the raw input data at it. They don't need explicit labels because we don't need labels, right? But the algorithm in itself, technically, it's supervised, correct? Because we have error back propagation, we have inputs, we have outputs, correct? We have reconstruction error, we adjust weights. So from algorithmic point of view, it's supervised, but from data point of view, it's unsupervised because we are not using labels in this case. So once we build this one, we will train it, and when we train it, we can just we slice it, correct? And we use the first part for data compression. This is the most important part. We don't need the decoder, in fact. The decoder is not important for us. The most important for us is the encoder, if we will use it for dimensionality reduction.
The decoder is again can be made for visualizing the picture after?
The decoder for reconstructing the image one more time. So this one, it's the original image. This one, it's the reconstructed. And this reconstructed, we reconstruct it using the compressed code, right? And we reconstruct it because we need to calculate reconstruction here. We don't need it. We just need it because we need to create reconstruction error, because we will subtract this one from this one, and the difference will be reconstruction error. And this reconstruction error will be used for updating the encoder parameters, the weight values. So this is the whole task for it. So in fact, we don't need the decoder. After training an autoencoder, we will slice it and we will use the first part. Only the first part is the most important for us, because the code is important for us.
We train weights in the encoder section, yes?
Yes.
And also we can save, for example, those weights for another model, yes?
Yes. If you want to use it for what?
For example, another model, another example.
But not another data set, because it's a data driven.
The same, yeah.
So if you will train it, because I can this one, the original image, it's 28. We can scale, we can sample. I mean, if I have a different dimension, we can make it okay for this one, but it will not perform well because it's a data driven. So if you trained it for landscape photos, you cannot use it for image data set. You cannot transfer it from one
Yes.
problem to another problem. But you can save the weights because I don't need to train the autoencoder each time, right? So once you trained it, you need to keep it, store it in your computer, for example, and use it each time when you have a new image. So if we will use this one with the problem, I need to keep the encoder all time because I will train a model using the code. So each time we need to generate the code. If you got a new example in the future and I want to classify it, I need to get the code of that example. So we need to keep this one all time. So after training our neural network, this part will be connected all time with the neural network. But I mean, I can put it in one neural network, in fact, using the encoder which we just trained, and we can freeze it. So we don't update the weights again of this layer. So I will have this part in my model, but we will not update it anymore. I just need to keep it like buffer, for example. So when we have an original image, this original image will be reduced into a code, and this code will be used for classification. So in this case, instead, imagine this one, it's 32 points. So instead of using the original image, which is very huge, I will just use a reduced set. So imagine it's autonomous car also, you are getting images, I mean, from, and you need to classify it quickly because you need to find road, landscape, people, trees, and stuff like this. So we can use it the same. We can train a model. I can train an encoder, for example. Use this encoder, and this encoder will compress all images into a code, and this code will be used for classification. So in this case, we can build, I mean, simpler model. And
the main aim is to avoid overfitting.
Yes, of course, to avoid overfitting. Yes, it's very, very important. We try to reduce all time to avoid overfitting, because when the model is we call it model capacity. So when the model has very high capacity, chances to overfit will be very, very high. So we try to, and also we try to get the most important, most interesting features, right? Because sometimes you have redundancy. As I told you in this example here, specifically in this example, we have lots of, it's a black and white, right? So it's just a black and white pixels, So, I mean, there are big areas without any knowledge for us. I mean, there's lots of areas which does not make any sense for us, right? So it's smart to try to reduce it to the most important features and use those most important features for decision making.
Hello,
Hello?
can you hear me?
Yes, I can hear you. Hamed, how are you?
Yeah, I'm good. Good morning. I have a question that in reducing the dimensions, are we going to lose some interesting information as well?
Yes, we will lose, of course. I mean, there is a cost, and the cost will be we will lose some because the reconstructed image, it will be like a loosey representation of the original one, right? So we will lose some information. It will be the graded representation of the original image. So we will lose something. But there is a trade-off between what we lose and what we gain, in fact. So if you will be able to represent your image using 32 bits instead of 784, maybe you will lose maybe 5% of the knowledge, but you will get the same accuracy. For example, if you can get the same accuracy, so it will be good decision to reduce the image into this small set of features.
Okay, thank you.
But we will lose. Of course, we will lose. So even in PCA, for example, we need to find cumulative variance, for example. So we need to know how much knowledge we still keep using 10 principal components, 15 principal components. If you want to keep it all, you need to use the whole set of eigenvectors, right? You need to keep it all. But the price will be very high because. But I can say, okay, I will keep 10. I will use the top 10, for example, and I will keep 80% of the data, of the information. But those 80% with this reduced model, I mean, the performance will be the same as using the whole set, right? So maybe the accuracy, maybe the model performance will go up. Maybe the training process will be cheaper, will be easy, much easier. You need a small set of data points, a small size of data set to train your model. So there is a trade-off all time between how much knowledge we will lose and how much gain we will get from simplifying the model itself.
Okay, thank you.
Thanks, Hamid. So we have here an example. I tried to build an autoencoder for iris dataset. As I told you, the autoencoder, it's just feed-forward the neural network, just feed-forward. You need to decide how many layers, right? We can start here with a very simple one. This very simple encoder, it's 2 layers, an input layer and an output layer, correct? So you have a data point, those data point, it's M-nested data set. So in case of M-nested data set, we have 784 data points because this is 28 times 28. So we will just use 2 layers. The first layer I will call it encoder layer, and the output layer will be decoder, right? So I can plot it here. So it will be like this one. I have an image. I mean, so the input, you can say it's input layer, but there is no something called input layer. So we have here x1, we have x2, we have here at the end x784, correct? So this is my image after we flatten it. Yes. So this image, in fact, it's 28 times 28, 28 times 28 pixels. We will just try to make it like this one. So
3 channels.
No, it's 1 channel. It's a
channel.
grayscale. So this one, it's 1 channel. So it will be a problem really if we need to make an encoder for because it will be much bigger, right? So, but it's not a problem. So the first layer, it will be, I selected here how many units? 32. So how many units, how many neurons in this layer? It will be 32, which means the code size is 32. So I will just make it. So I will just make it like this one because to look like we have a bottleneck, right? So this one will be 1, 2 until 32. Correct? We will connect all those. Just connect all data points to those 32 values, right? Correct. So now we call it, this is the code, correct? This one will be the code. What will be the output layer? I need to reconstruct one more time. So the output layer will be the same size as the input layer. So here we will have
700.
2, yes. 784. This one it's 1 and 2. So this one will be the reconstructed image, right? Just make all those connections. make all those connections. So now we have, this is the bottleneck. So we have an input image, and in the output here, we just reshape this one into an image. So this one can be reshaped again into an image of the same size. This one will be reconstructed image, correct? So we will reshape this one again into. So this is feed-forward neural network. So this one, I call it encoder. And this one, I will call it decoder. So we have 2 layers, just 2 layers. How can we reconstruct this one in Keras, for example? It's easy, it's dense layer, so it will be dense. Number of units will be 32, and the shape of the input will be just simple, it's this number. You can select, for example, activation RELU, for example, activation function, it will be, for example, RELU, and just for this one, right, it will be also dense layer, and this dense layer, it will have how many units, how many neurons? It will be 784, right? It will be this. So now we have feed-forward the neural network. So the input will be an image, the output will be a reconstructed image. We will subtract this one from this one to get something called reconstruction error. This reconstruction error will be used by error backpropagation to adjust the mix. And we will train the model until we have good performance. So we have here in the, I just selected sequential API, which is very easy. I just like it because in Keras it's easy and it's more common, but we have model also. So we will use sequential. So the first layer, it will have 32 units. The activation function will be linear. I mean, it's okay because this is pixel values and all pixel values are positive. So in fact, we don't need to use RELU, correct? You can just use RELU, it's okay. I'm not expecting any difference if you use RELU here, right?
Sorry, I just want to ask, because the sequential, what is the difference between the sequential and the feed-forward? Because the feed-forward is...
No, it's in Keras, it's a feed-forward. We are doing it. Okay. This one, it's feed-forward. But in Keras, they have this API, which called sequential, for reconstructing the model. So the model will be a stack of layers.
Yeah.
So you just start with this sequential, and after that, you will define your layers, layer by layer. So at the end, the model will be a stack of layers.
Because I have worked with sequential, but I was just trying to Google yesterday, like what's the difference between sequential and feed-forward, and there is no
difference.
No difference.
No. This is how they programmed it, how they prepared it for programming. So we can use it even for deep learning. Deep learning also, we will have a stack of layers. So sequential here, it will be a stack of layers. So just to define, this is a model. So the model will be sequential. And you need to just define the autoencoder equal sequential and the autoencoder equal dot add. We need to add layers, layer by layer. So at the end, the model will be a stack of layers. This one will be the first layer. This one will be the second. We have something, we have input layer here, but it's no problem because the input layer doesn't do anything. It's just a transfer input to this layer. So we will have this one. So the input dimension here will be 784. You can give it a name, for example, encoder layer, for example. You need to select this activation function. You need to select the number of units. The output layer also will be the same size as original image, right? And you need to select this activation. You need to give it a name, or you don't need to do it. And after that, we will compile. So after doing this, you need to compile your model. You need to select this optimizer. You need to select the loss function, right, which we need to minimize. And that is it. And after that, you can use autoencoder summary or model, plot model. This plot model, it will give you this graph. So just to double check if your model is okay, right? It will give you all information, or you can get this table also. This table is nice because it will give you all number of parameters, trainable parameters. How can we find number of trainable parameters? So the encoder layer, it will have this number of parameters. The decoder layer will have this number of parameters. Can you calculate this number? Can you do it for? Yes, can you calculate it?
Yeah, 32 multiplied by 784 plus 32.
Plus, very good. And this one, it will be
784
times
784.
Times 32. Plus 784. So this number is greater than this number, right? So it's here. So it's a number of units.
We have in the second layer, we have 32 neurons.
Yes, 32 times 784 plus 784. I think I can just, they don't see them. I think we cannot make
Press one.
one.
Yes.
Okay. Oh, this is very good. Who made it? Yes. So to calculate number of weights, it will be number of units multiplied by number of inputs plus number of units bias. For the output layer also, it will be number of outputs multiplied by number of inputs plus number of bias to get those trainable parameters. So we will train it. So the idea here, it's unsupervised. It's in fact it's supervised and unsupervised. Just not. So when we train it, the input will be X-train and the output will be X-train, correct? Because this is autoencoder. So the output will be the same as the output. So the input will be X-train and the labels, it will be also X-train. You need to select the number of epochs, batch size, if you need to shuffle and so on. So, and just to train your model. And finally, we will get those outputs. So now we have, for example, I just upload some examples. We have 7, for example. This one will be the encode, this one will be the code. This one will be reconstructed image. And as you can see here, reconstructed image, it's a degraded image of the input. Yeah. So do you see it, Hamad? So the input, this is the original image. This is the code, which is, but as you can see, it's number 2. Okay.
They have the slides.
Okay. So we have here, this is 7, the original image. We have here the code, correct? So now this code will be reduced the set of the image. And this is the reconstructed image using this one. Right. So, and as you can see here, reconstructed image, it's degraded version of the original image because we are reconstructed it using a reduced information effect. If you want to improve this one, maybe you need to increase the size of the code, for example. Maybe you need to make your model more complex, correct? So I will have another example, but this is how. So this is compression. In fact, we compress the data into this code, and after that, using this code to reconstruct it one more time.
Just, I have another question. Because I was playing with a small algorithm yesterday, and when it comes to the total number of parameters, they have also included the number of the hidden layers. But here, for example, the total number of parameters, they only included the inputs and the outputs. The hidden layer was not part of the total number of parameters.
No, we have a hidden layer here.
We have
one, but only one hidden layer. So look in the model here. So we have an input layer, we have a hidden layer, and we have an output layer.
But the number of parameters, have we included the hidden layer?
Yes. Yes. We included it. So number of parameters of this hidden layer, it will be 32 times the input, which is 784 plus 32.
Okay.
And for the output layer, it will be 784 times 32
plus 784. Okay.
Yes, so we are including it.
Yeah. Another question. Okay, you can.
No. It's just after training this one, I will slice it. I will use only this one as a dimensional reduction. So in this case, all input images coming in, it will be converted, it will be reduced into, after training this one. Now this one has been trained. So now this one will be able to compress any image. So after training your autoencoder, we will use the first layer, right, for the encoder layer for just encoding any images into reduce the set. And then we will use this code for classification, for training another model for classification. So now instead of working with 784, I can work with 32. And you can just imagine how much reduction of parameters. It's a huge, correct? Because if I want to work with those full set, so the hidden layer should be larger, it should be large, right? Maybe we need to use deep, we need to go deep, 2 hidden layers, for example, so the number will be crazy. Now when we use the code, maybe we are reducing complexity by 90% or 80%.
When we use another challenge, for example, 3 channels, the number of parameters will be varied?
Yes, no, of course it will be different. I mean, each problem we design each problem for this problem.
And also we can use the sequential for that or not?
Yes, of course, the sequential for it. It's just for any model. If you want to go for keras, you need to use sequential all time or model. There are two ways. You can build using API called model or sequential. But
And
sequential is easy one.
for example,
For the three channel, I want to answer this question first. For the three channel, do you really my model needs those three channel? Because I'm compressing it. We are compressing it. So
the result is the same if you compress the image. For example, you have a RGB image,
yes,
3 channels, and the result is the same when you use, for example, gray one.
Yes, I mean, because for the model itself, we train the model to get a reduced set, right? So for the RGB, maybe I need to get this code also, right?
Yes.
I don't care about
the nature of MNIST is the
it's one channel.
One channel.
One
But
channel.
in the real world, we have a lot of RGB images, and it is better, for example, to use 3 channels in order to get more realistic results.
It's for us as a human, but for the machine, it's another story. Correct?
No. For example, if we reduce the image to the gray one, like
Yes.
MNIST,
Yes.
this
No, I mean,
better, or for example, use the original image.
We use the original image and we will reduce it into a code, right?
Yeah.
And I don't know how the code will look like, but this is something useful for the machine, not for us. Those RGB colors maybe are important for us.
You mean this is more understandable for machine?
Yes, why not? No one knows, correct? Because we try to get a code which makes sense for the machine, not us. Because I don't care if the machine, because maybe the machine is blind. I mean, it will not differentiate between green and the red and its features, right? We're working with features. So when we're studying deep learning, we try to get this feature map. So maybe this one is a feature map, correct? We don't know. I mean, it's a reduced set for. It's not only for images. I mean, we can use the autoencoder for any kind of data. So if you are working with banking system and you are working with an example with 100 features, you can use also autoencoder. It's not for images, it's for anything, correct? For RGB image, we have 3 channels, but do you think those 3 channels are important for the machine to classify? Is it important? I don't care. I need to reduce it into a subset of features so the machine can be more simple and right. So even in deep learning, maybe the original image it's 3 layers, it's 3 channels, but the first feature map it will not be 3 channel anyway. I don't need to keep those 3 channels. We will select a filter to deal with the 3 channels to get 2-dimensional feature map, right? It will be 1 channel feature map. Right?
Yeah,
we will have example for maybe next week and week after in deep learning.
Yeah.
I mean those colors are important for us, not for the machine.
Excuse me?
Yes, Hamad?
I have seen in many deep learning algorithms, like mostly even if we have the RGB data, they are converted to grayscale to reduce the complexity.
Yes, in the first convolutional layer. In fact, you're right, Hamad. In the first convolutional layer, we select a filter, 3D filter.
Yes, I know.
This 3D filter will convert it into a grayscale feature map, right? So we will get rid of those 3 channels. So those 3 channels will remain in the first layer only after the first. So after the first layer, we won't have any 3 channels anymore. Maybe we will have 64. Maybe we'll have 32 channels, but those feature maps, not the original image. So because in the input in the first convolutional layer, we will select a filter. It's a 3D filter, 3 times 3 times 3, for example.
I know.
This one will deal with the 3 channels, and we will not have any 3 channels later on. We will get some different feature maps, and we will try to abstract and get more higher level, abstraction of those feature maps, which makes sense for the model, right?
Yes.
So it's the same here also. If it is 3D, if you have 3 channels, maybe we can do something here, or we can just flatten it and reduce it into this one. And we will spend more time for training the autoencoder to get something representative of of each image, for example. So this one will make sense more to the model. We hope this, right?
Yeah.
And just imagine how much reduction we will get. And it's all time it's a trade-off. We need to make this hard decision. I mean, how much reduction do we need? But as Hamad mentioned also, when we reduce, we will lose some information. We will lose knowledge. And you can see it here. This one, it's a reconstructed image.
Yes, I care about that losing. Yes.
Yes. So we will lose something, but I mean, at the cost of having a more simple model, and because when it's simple, we will avoid lots of problems, right? Maybe even also in the implementation and in the production. We're building a model for quadcopter, right? So how much weights we need, how much processing on board we need, right? We need to make something simple because the quadcopter, it needs to make some decisions, and it does not have so much memory and the computational resources on board, right?
Yes, I know.
So we need to.
Yeah, I know.
So what the machine is, maybe the machine is interested in something different. They don't care about colors and stuff, and they don't differentiate between red and blue. And so the most important maybe it's the features which we will extract from the image, right?
Yes.
Yes. So so finally we will have this original. This is the encoded. This is reconstructed, and we can see that the constructed image, it's a loosey representation of the original image. So I want to go for deep autoencoder. Just a deep, it's not. It's just increasing number of layers. When we go deep, it means we just increase. This one, it's not deep because we have only 2 layers. We have an input layer, we have a hidden layer, and we have an output layer. If you need to increase, maybe you can increase one layer here and one layer here. So in this case, we can say that it's a deep autoencoder. So deep autoencoder, I defined, we have an input layer. This one, it's the encoder layer 1, encoder layer 2, encoder layer 3. So I will just select, it will be 6 layers, right? When we go deeply, it means we're increasing the number of hidden layers. So last time we had two layers. It's one hidden layer and one output layer. Here, it will be 6 layers for encoder, 6 layers for decoder, right? We go deeply. And when you go deep, maybe your chances to, to map more complex patterns and learn a more difficult mapping between inputs and outputs, it will be much better. So we will compare results. So this one, we will have now 6 layers. So it's 1, 2, 3, 4, 5, 6. As you can see here, when we go deeply, number of parameters will increase a lot, correct? So total number of parameters will be, it will be 222,000 parameters. So when number of parameters increases, the chances to overfit is there because now it's more complex, correct? So, but maybe my problem is difficult, right? Maybe we have, difficult objects in my images. We need to really classify many complex, things in the image. So in this case, maybe we need to go deeply. So I will just define this one as a deep autoencoder, and it's just the same. So the first block here, will be the autoencoder. The second block will be the decoder. I will combine, summarize my model, and train my model. I guess I want to go to something. So this is very important, right? I want to slice my model because after training your autoencoder, we need to slice it. I need to extract the autoencoder, the encoder only. So the encoder will be the first 3 layers. So how can we do this? You just need to define a new model here, in fact, right? Just to define a new model. I will call it model. We have also something called the model API. So I have the encoded input. It's the input to my encoder, right? Encoded input. Oh no, this one. This is the encoder. This is the decoder. So the encoder, in fact, it's the input will be the input to the autoencoder, right? And I want to get the output from the 3rd layer. So here, in fact, underneath this one, if you can see it online, we just need to get the output from the 3rd layer, right? So this one will be, so encoded image, we will get it from encoder.predict text, for example. So this is the one which we are interested in. So after training your autoencoder, you need to slice it, and you need to get the outputs from the 3rd layer, because the output from the 3rd layer will be the code, correct? So you have the original image, you have the encoded image. So the encoded image or the code will be the output from the third layer. So I just did it using a model. So the input to the model will be the input to the autoencoder, and the output will be the output from the third layer. I can just remove this one. Because this one is very important. How can we slice? Okay. Denoising. Can you see it? Do you see? Okay. Do you see it now? So the output, because we need to get the output from the encoder. So the output from the encoder will be this layer. So this is the code. So if you want to get the code, in practical, after training your model, I want to deploy it. So in deployment, I want to get the output, this output. How can we get this one? It will be the output from layer number 2. Correct? In this deep autoencoder, because in deep autoencoder we have 6 layers. So it will be 0, 1, 2. So just remember the order. If you want to get the output from the third layer, it will be layer number 2. The index here will be 2, because we have 0, 1, 2. So it will be 2. So in this case, we can get the code from this one. So I just need to apply the inputs and get the code, because it has been trained already. If you want to, for reconstruction also, you can extract this one also for reconstruction if you want, right? But we are not interested in the decoder. We are interested in the encoder, because we need to use it for coding. So maybe this one, it looks much better, maybe. Reconstruction, because it's a deep autoencoder, so I don't know, but it's still also degraded image of the original image.
We can choose to encode from whatever layer we want.
Yes.
Okay.
From it's because of course, but the bottleneck, the one in the middle, because I need to reduce the dimension from 784 into 32. So here in this design, I selected 6 layers. So you just select which one you want to use. Of course, it will be the one in the middle, because we need to reduce, right? So the input to the model will be the input, and the output will be the output from this layer. If you want to extract only that part. So now, after training your model, you just store your weights somewhere. You just use this part for encoding any new images, because the idea here is to train my model as a classifier, for example, and test it with new data. So in production, I will use this encoder all time. It will be like the buffer. The input will be applied to this image, and then we will get the code. And this code will be applied to my model. So this one is very, very important. Do you want to take a break? Okay. So we will take 10 minutes break, or.
Ben jij nog wat chartbol? Ja, gewoon toedoen. Als leuk voor is toe. Dat is weer. Tegen wat in minus toe posen. En dat is komt u zo. Zo heb ik minus toe. Het had ik van training voor. Geen van